Torque and angular momentum. Torque about point. Torque vector is equal to r vector into f vector. Magnitude of torque force into perpendicular distance of line of action of force from the axis of rotation. T is equal to r f sin theta. Directions of torque can be determined by using right hand thumb rule. Rotational equilibrium. If a body is at rest or it moves with constant velocity in a particular direction, it is said to be in translational equilibrium. A body is said to be in translational equilibrium when the vector sum of all the forces external acting on the body is zero. For translational equilibrium, f vector is equal to 0 f vector is equal to dp vector upon dt is equal to 0. P vector is equal to constant, where p vector linear momentum of the body. If a body rotates with a constant angular velocity, the body is said to be in rotational equilibrium. For rotational equilibrium, torque net is equal to 0. dl vector upon dt is equal to 0. L vector is equal to constant. Principle of momentum. When algebraic sum of the moments of all forces acting on the body about a fixed point is 0, the body will be in rotational equilibrium. This is known as principle of moments. Principle of moments. Considered an ideal level comprising a light rod AB of negligible mass pivoted at a point O as shown in figure. For translational equilibrium, torque net is equal to 0. Torque 1 is equal to torque 2. F1 into D1 is equal to F2 into D2. Load into load arm is equal to effort into effort arm. Mechanical advantage MA is equal to load in bracket I F1 effort F2 is equal to D2 upon D1. A small effort is applied to lift a heavy load of MA is greater than 1, that is D2 is greater than D1. Center of gravity. A point where the height of the body acts and total gravitational torque on the body is 0 is known as the center of gravity. Moment of inertia. Moment of inertia is analog of mass in rotational motions. The physical quantity measuring the inertia of rotational motion of a body is known as the moment of inertia. Consider the motions of a rigid body rotating about an axis as shown with angular velocity omega. The linear velocity of particle of masses m1, m2, m3 and so on as mn are v1, v2 and so on as vn respectively. Total kinetic energy of the system is Ke is equal to 1 upon 2 m1 v1 square plus 1 upon 2 m2 v2 square plus 1 upon 2 mn vn square, or Ke is equal to 1 upon 2 n I is equal to 1 mi vi square, as vi is not the same for all particles, so we can substitute vi is equal to omega r I. Therefore we have Ke is equal to summations 1 upon 2 mi omega r I square whole in bracket square is equal to 1 upon 2 summations mi r I square in bracket omega square. Moments of inertia in rotational motions. The analog of inertial mass is summations mi ri square, which is termed as moment of inertia I, that is I is equal to summations mi ri square. From equations I, Ke is equal to 1 upon 2 I omega square. Thus for continuous distributions of particles in a body, I is equal to integrations r square dm. SI unit of moment of inertia is kg meter square. Radius of gyrations k. The distance from the axis of rotations at which, if the whole mass of a body is supposed to be concentrated, the moment of inertia would be the same as the actual distributions of mass of the body. K is equal to under root r1 square plus r2 square plus r3 square plus rn square upon n. Moment of inertia in term of radius of gyrations is I is equal to mk square. I is equal to mk square. Angular momentum moment of linear momentum. Angular momentum of particle about a given axis is the product of its linear momentum and perpendicular distance of line of actions of linear momentum vector from the axis of rotation. L vector is equal to r vector into p vector. Magnitude of angular momentum. Linear momentum into perpendicular distance of line of actions of momentum from the axis of rotations. L is equal to mv into r sin theta. Directions of angular momentum can be used by using right hand thumb rule. In angular momentum, according to Newton's second law for the rotatory motions, torque vector is equal to delta L vector upon delta T is equal to I alpha vector. The angular impulse is equal to change in angular momentum. If a large torque acts on a body for a small time, then angular impulse is equal to torque vector delta T. Conservations of angular momentum. Angular momentum of particle or a system remains constant if torque external is equal to 0 about that point or axis of rotations. If torque is equal to 0, then del L upon del T is equal to 0. L is equal to constant. If LF is equal to Li, or I1 omega 1 is equal to I2 omega 2. Rotational kinetic energy of rotation, kinetic energy R is equal to 1 upon 2 I omega square. Other forms K is equal to 1 upon 2 I omega square is equal to L square upon 2I is equal to 1 upon 2 L omega. If external torque acting on a body is equal to 0, torque is equal to 0, L constant, K inversely proportion I, K is directly proportion omega. Rotational work omega R is equal to torque theta. If torque is constant, omega R is equal to integration theta 1 theta 2 theta 2 torque d theta. If torque is variable, the work done by torque is equal to change in kinetic energy of rotations. Omega is equal to 1 upon 2 I omega square minus 1 upon 2 I omega 1 square is equal to 1 upon 2 I omega square 2 minus omega 1 square. Instantaneous power is equal to dw upon dt is equal to torque d theta upon dt, torque omega. Average power P average is equal to P average is equal to del omega upon del T. Comparison of translations and rotational motions. Linear motions, rotational motions about a fixed axis. Displacement x, angular displacement theta. Velocity v is equal to dx upon dt. Angular velocity omega is equal to d theta upon del t. Accelerations a is equal to del v upon del t. Angular accelerations alpha is equal to del omega upon del t. Mass m, moment of inertia I, force F is equal to ma, torque is equal to I alpha, work omega is equal to Fs, work W is equal to torque del theta. Kinetic energy K is equal to mv square upon 2. Kinetic energy K is equal to I omega square upon 2. Power P is equal to Fv. Power P is equal to Fv. Power P is equal to torque omega. Linear momentum P is equal to mv. Angular momentum L is equal to I omega. Combined translational and rotational motions of a rigid body. When a body performs translatory motions as well as rotatory motions, then it is known as rolling. Contact point, pure rolling Vcm is equal to R omega Cm. In pure rolling, if the velocity of point of contact with the respect to the surface is zero, then it is known as pure rolling. If a body is if a body is performing rolling, then the velocity of any point of body with respect to the surface is given by v vector is equal to v vector center of mass plus omega vector center of mass into r vector. Now only translatory motions plus only rotatory motions is equal to rolling motions. Va is equal to 2v center of mass, Ve is equal to under root 2 v center of mass, Vf is equal to under root 2 v center of mass. For pure rolling above body, Vv is equal to 0. Velocity at a point on rim of a sphere, Vnet is equal to under root v square plus r square omega square plus 2v r omega cos theta. Rolling kinetic energy under pure rolling body surface, v center of mass, rolling kinetic energy E is equal to 1 upon 2 mv square plus 1 upon 2 I omega square is equal to 1 upon 2 mv square plus 1 upon 2 mk square in bracket b square upon r square. Rolling kinetic energy E is equal to 1 upon 2 mv square in bracket 1 plus k square upon r square. E translations ratio E rotation ratio E total 1 ratio k square upon p square ratio 1 plus k square upon r square 1 ratio k square upon r square ratio 1 plus k square upon r square ratio. Body k square upon r square E translations upon E rotations is equal to 1 upon k square upon r square. E translations upon E total is equal to 1 upon 1 plus k square upon r square. E rotations upon E total is equal to k square upon r square upon 1 plus k square upon r square. Ring 1 1 upon 2 1 upon 2 disc 1 upon 2 2 2 upon 3 1 upon 3 solid sphere 2 upon 5 solid sphere 5 upon 2 5 upon 7 2 upon 7 spherical cell 2 upon 3 3 upon 2 3 upon 5 2 upon 5 solid cylinder 1 upon 2 2 2 upon 3 1 upon 3 hollow cylinder 1 1 1 upon 2 1 upon 2. Motions of a spherical body on a rough inclined surface. Minimum value of coefficient of frictions required for pure rolling. Mu minimum is equal to tan theta upon 1 plus mr square upon I. If mu is equal to 0, body will slip downwards. Only translational motions with an acceleration a1 is equal to g sin theta. If mu is greater than mu minimum, then body will roll down without slipping with an acceleration rotations plus translation both rotations plus translation both. A2 is equal to g sin theta upon 1 plus I upon mr square. When mu is greater than mu minimum, force of frictions will act upward. Magnitude of this force is F is equal to mg sin theta upon 1 plus mr square upon I. If mu is smaller than mu minimum, body will roll downwards with forward slipping. Maximum frictions will act. In this case, the accelerated of body is A3 is equal to g sin theta minus mu g cos theta. Comparison of pure rolling and pure sliding on an inclined on physical quantities. Pure rolling, pure sliding, accelerations. Physical quantity accelerations. Pure rolling g sin theta upon 1 plus k square upon r square. Pure sliding g sin theta. Velocity under root 2 gh upon 1 plus k square upon r square. Under root 2 gh. Time taken to cover the distance is, where k is the radius of gyrations. Under root 2s in bracket 1 plus k square upon r square upon g sin theta. Under root 2s upon g sin theta.